Hello everyone and welcome to today's video. Today we are going to discuss how we can use K-means clustering, which is an unsupervised clustering algorithm for anomaly detection. So let's go ahead. So in the left hand side, we can see that how the K-means clustering works. Suppose we have many clusters. So if we run the K-means clustering, iteratively the cluster center will fall into the center of the actual clusters. And according to the distance of each point from that cluster, we can classify them from cluster 1, cluster 2, cluster 3, cluster 4. So how we can use that for anomaly detection? So let's say, so let's say, for the anomaly detection, we'll take our number of cluster k should be equal to 1. We only have one cluster which belongs to the normal dataset, and according to that, uh, we will do the anomaly detection. So this is our normal dataset where we got the cluster by running the K-means clustering algorithm, and then from each point in the normal dataset, we'll calculate the distance from the cluster center. So let's call that D. So we'll obtain a value of D for the entire set of normal dataset, and then when there will be an anomaly, the distance from the cluster center would be pretty high. So by comparing that distance of the anomaly with the mean distance, or let's say the mean distance of the normal data set, we can say, okay, this data may be an anomalous because the distance from the cluster center is pretty high. So let's see how we're going to execute this in the Jupyter notebook. So as with all the previous video, first we import the necessary libraries, then we'll import the dataset for both fault-free and faulty condition. We'll concatenate them both. So finally our dataset looks something like this, where we have all the fault number and 500 simulation run for each fault. Then we'll scale the dataset. This is important because K-means is a distance-based algorithm, and if we don't scale, then the feature which is a higher range, they will be much impacted. They will have higher impact on the distance calculation. So that's why scaling is important. After we scaled the dataset, we are only using the fault-free data that we are putting it here, fault-free scaled. Now we'll run our K-means algorithm. So we'll import the K-means clustering, then define the number of cluster. Because we know we have only normal data, we are training it only on normal data. So we are putting K equal to 1, cluster center. And then we are initializing our K-means clustering where n clusters equal to K, which is 1 here. We're using that instance to fit on our fault-free scaled data, this one here, to get the k-means. After training the k-means algorithm, we can just write k-means dot cluster centers to obtain the center, and here the center will be a 52 dimensional vector because we have 52 sensor variables here. So this is how the cluster center looks like. And now we are going to calculate the distance with respect to this cluster center in order to know whether the data belongs to normal condition or faulty condition. For that, I'm importing another library called pairwise distances. This pairwise distances will calculate individual distance between two points. So from this cluster center to any point in my dataset. So I'm creating this function, which means distance from center. My input will be cluster center and the dataset from which I want to calculate the distance. I'm initializing a list of distances and I'm iterating through each and every element of the element x. Then when I'm writing dist equal to pairwise distance, and this pairwise distance function will take two inputs. One is the cluster center and the another point from which we need to calculate the distance. This basically will calculate the Euclidean distance and save in the variable dist. Then I'm just going to append this in my list pdist, and finally I'm going to convert that into an array and reshaping. In the next step, I'm just going to see this distance, the histogram of this distance for the normal, the fault-free data. First, I'll import the fault-free data, scale them, Then I'm going to pass them through this function, distance from center. One of my input will be the cluster center and another will be this dataset, and it will give a list of distance from the cluster center. If I put it in a histogram, I can see that most of its distance belongs to like six or seven, and yeah, it basically follows a normal distribution. If I want to calculate the threshold for this entire histogram, I'll calculate the threshold by mu plus 2 standard deviation, which comes to be 9.423. So if the distance is higher than this, I'll say, okay, that belongs to a anomalous condition because that is far from the cluster where my normal data lies. If that is clear, then I'm just going to plot, the distance, the pairwise distance of each data point for different fault scenarios. For that, I'm going to iterate through different fault number, import the data, scale the data, and then pass it through distance from center. So what way will I get? So for fault 0, this is my threshold that I just calculated, which is 9.423. The black line is the threshold. If the pairwise distance passes this threshold, that means that is anomalous. For fault 0, we can see, or the fault free case, all the data lies within that, which is a good sign. For fault number 1, as soon as the fault has been introduced, the pairwise distance passes the threshold. Same for fault number 2, but fault number 3 we cannot detect it. Yeah. Similarly, it goes for different type of fault, and it does a pretty good job. And it's the algorithm is very simple as well. We don't have to train any complicated neural network. All right, or not like the ensemble method we did in a brief video, which is pretty complicated. But this one is pretty straightforward and simple. Then I want to create a single matrix, single F1 score. So what will I do? I create this function. So this function will generate 1 if the value passes the threshold. If x is greater than threshold, then it will generate 1. And then I'm converting that to a float variable, float data. And in order to get the performance of this method on the entire dataset, I'm creating this function. So what will this function do? It will iterate through each fault except for fault 3 and fault 9 because they are very difficult to identify. First, get the dataset, scale them, pass them through the distance from center function, which will get the pairwise distance. Then use that in this combined result function, where one will be this faulty distance and another will be threshold, another input will be threshold, and it will give a boolean or 0 1 matrix, 0 for no fault condition, 1 for faulty condition. Then I'm creating the truth table, like the truth condition for when f num equal to 0, all value will be 0. When there will be any other fault, then it will be 1 except for first 20 sample. Then I'm importing the matrices and I'm just obtaining the F1 score and accuracy. So you can see that for various method we got different accuracies. And finally, I'm averaging them out. So in the end, what we got is F1 score for the Kmeans method is 0.612 and accuracy score is 0.717. So now if we go to my GitHub, you can check the benchmark I created. And here you can see that for the K-means based algorithm, this was 0.612 and accuracy is 0.717, which is comparable to autoencoder based reconstruction and PCA based reconstruction, but not very good in that. Still, till now, I'd still prefer the statistical method or the ensemble learning method. In the next video, we'll see how we can use one class SVM and isolation forest for anomaly detection.